Swayam Prabha. Digital India. Educated India.
I welcome you all to the session of thermal engineering basic and applied. Today we shall discuss about a simple float type carburetor. By depicting the geometrical configuration of this particular type of carburetor, we shall discuss the flow analysis, because we have seen carburetor is a special device and this particular device is integrated with the internal combustion engine, that is the spark ignition engine, and the sole purpose of this device is to supply homogeneous mixture of air and fuel. So, we have understood by this time is that carburetor is provided to ensure that engine will get chemically correct or the stoichiometric air fuel ratio. In the last class we have also discussed it is very unlikely that engine will always get stoichiometric air fuel ratio. Instead, considering several regimes of engine operation, we have discussed that carburetor would be able to provide air fuel mixture or fuel air mixture in a given range, and that is the combustible range of any particular type of fuel. So, sometimes it may be higher than the stoichiometric ratio or it may be lesser than the stoichiometric ratio. So, today what we will do, we shall draw a simple float type carburetor, then we shall go for its analysis. So, if we try to draw the simple float type carburetor, if we draw here, it is not exactly at the middle. So, let us try to draw it. This is section AA. Through this section air is taken. Now, this particular element is Okay. Now, I would like to show it one float valve. So, this is float valve, this is air vent. This air vent is provided to ensure that this is fuel tank. So, basically fuel is open to atmosphere. So, the pressure acting on the fuel surface is atmospheric pressure. This is the path through which fuel from tank. So, fuel from tank is taken to this reservoir through this line, and this is basically float chamber. So, this is the float chamber. You know that fuel is coming from fuel tank through this line and it is entering into this float chamber, and this is the float. This is the float. You have seen in daily life the application of float valve. So, this is float, right, and if we see, this is, so idea is, you know, that though it is not complete, but we have, say, here one, if I draw one, this is the throttle valve, and then two engine cylinder. So, this is basically intake manifold, you can say. So, this is the intake manifold. Now, let us briefly discuss. Idea is air will come through this manifold, of course, air cleaner should be there. So, clean air is taken. Now, we need to have some arrangement so that air will flow through this flow path, and while air is flowing, you can understand this is open to atmosphere, this is also air vent. So, this the pressure acting on the fuel surface is also atmosphere. We need to create, so air will flow through this, you know, path, through this path, and while air is flowing, we also need to have simultaneous flow of fuel from float chamber into this particular pathway through this particular, you know, system, and that is known as orifice. So, this is calibrated orifice, and this is tip of orifice. Okay. And so, this is section BB. What did I say? I said that when air will flow through this pathway, the flow of air also will try to induce, or flow of air also will try to induct certain amount of fuel that is required for that specific operation from float chamber into this pathway, that is some fuel will be injected through this calibrated orifice and it will be discharged at the tip of the orifice. So, we need to make some arrangement through this simple float type carburetor that simultaneous flow, air and fuel will have simultaneous flow. So, air will flow from the air cleaner, that is clean air should be taken to remove all the dust particles which are there in the air, and the flow of air also will try to induct certain amount of fuel from the float chamber through this calibrated orifice, and that metering fuel should be discharged at the tip of the orifice. By how we can do it? Because this is also open to atmosphere, this is also open to atmosphere. So, we need to have some kind of pressure difference. So, when air is flowing through this particular pathway, if we can somehow made, or if we can somehow make an arrangement that the flow of air will also create a pressure difference between the float chamber and tip of the orifice, and that pressure difference will allow liquid fuel to flow through this calibrated orifice and fuel will be discharged at the tip of the orifice. By how? So, to have this, we need to have some constricted passage, and that constricted passage will reduce the pressure and it will increase the velocity. So, that means air is coming from top. If we can somehow increase the velocity of air in this location where tip of the orifice is there, and that increased velocity will lead to a drop in pressure, and that pressure difference, because this is the atmospheric pressure, if we can reduce the pressure at the tip of the orifice less than atmospheric pressure, that pressure difference will allow liquid fuel to flow from float chamber through the calibrated orifice and up to this point, that is tip of the orifice. So, what we can do, this is done, you have studied in fluid mechanics that what we need to do, we need to provide venturi. We need to provide venturi. Okay. So, we are providing venturi. What it does? The venturi is essentially reducing the flow area. So, when the air will approach this venturi, velocity will increase, that is flow will accelerate. At the cost of this accelerated flow, pressure will drop, and the drop in pressure should be such that the pressure difference between float chamber and at the tip of the orifice is the driving force for the flow of fuel from float chamber into this point, up to this point. So, this is let me write here, this is basically fuel. So, this is fuel. Okay. Now, we need to know the drop in pressure exactly at the tip of the orifice, rather in this location. What we can do? We can measure this drop in pressure by connecting a manometer here. So, let me here. So, this is P atmospheric. So, you can understand this is P atmospheric, and pressure at this junction will be less than atmospheric by this height, and that we can measure what is the pressure by measuring the rise of the manometric liquid in this U tube manometer, and we can calculate what is the pressure drop, and whether that pressure drop is sufficient to have flow of fuel considering fuel viscosity, surface tension, etc. Because when fuel will flow from float chamber through this calibrated orifice up to the tip of the orifice, accounting for the frictional loss due to viscosity of the fuel as well as surface tension, we need to design the venturi accordingly. Okay. Now, so basically you see that when liquid fuel is trying to say this is the fuel initial height. Okay. So, this is the fuel initial height, I should this is the fuel initial height. Okay. So, this distance which is, so this distance is delta H. So, this is delta H. So, we need to overcome this static height delta H together with the frictional loss as well as surface tension effect. So, pressure difference should be such that we can overcome the frictional loss effect that will be there due to surface tension as well as the static height. So, that liquid fuel will be injected at this location. So, this is the venturi, center of the venturi. So, this is basically the idea. Now, let us you see that the flow of air is there, clean air, because the air should be taken through cleaner, air cleaner, so that dust particle will be removed. So, clean air is flowing, the flow of air is now simultaneously inducting liquid to be metered from fuel chamber into this venturi, and the fuel that is being injected will be atomized and will be convected by the air flow. So, good thing is the reduction in pressure will allow liquid fuel to flow from this chamber to this particular point. The moment when fuel is getting injected, here the velocity of air is even more. So, the high velocity of air will try to atomize the fuel which is being injected here. Not only that, and that will be convected. So, basically that fuel which is atomized. So, fuel evaporation will start from this particular part of this venturi, part of the carburetor, and that atomized fuel also will be convected by the air stream further downstream, and it will go to the engine cylinder. So, this is basically the throttle valve that is given. We have seen the utility of this particular component, because we need to have almost closed throttle valve during idling condition. So, by tuning this throttle valve opening area, we also can control the pressure difference, right. Maybe this port is, this particular manifold is connected to the engine cylinder. So, when piston will come from TDC to BDC, we are creating pressure drop inside the engine cylinder, provided this throttle valve is fully open. If the throttle valve is not fully open, though we are creating pressure difference inside the cylinder by bringing piston from TDC to BDC, that pressure difference will not be felt by the air which will flow from air cleaner through the venturi towards the engine cylinder. So, that is given, because to meter the amount of fuel air mixture to be supplied to the engine depending on the load. So, this is all about the simple float type carburetor. Idea is we need to supply air fuel mixture. So, we are getting clean air, we are getting fuel from this, and ultimately in this position we are getting air plus fuel. So, this is air plus fuel. Okay. So, this is the idea. So, now let us quickly do the analysis. So, basically what would be the mass flow rate of air and mass flow rate of fuel? We are interested in the mass flow rate of fuel as well as mass flow rate of air. So, this is mass flow rate of air and this is mass flow rate of fuel. So, these two quantities are very important to know whether this simple float type carburetor is able to meet the demand of the engine or not, whether this simple float type carburetor is able to meet the demand of the engine or not. So, let us now look at the mathematical expression of the mass flow rate, and by what we have understood that flow rate will be also controlled by the size of the venturi, because we need to calculate mass flow rate of air and mass flow rate of fuel exactly at this junction. So, the geometrical configuration a geometrical dimension of the venturi will dictate the mass flow rate of air, which in turn will also control the mass flow rate of fuel, right. And whether mass flow rate of fuel is sufficient or not, that is determined by the pressure drop, and to do that we have connected one U tube manometer over here. So, if we apply now steady state steady flow energy equation, right. So, basically if we go to the previous slide, so this is B B and this is A. So, if we apply steady flow energy equation between sections A and section B B to calculate what is the mass flow rate of air, right, because we need to calculate mass flow rate of air as well as mass flow rate of fuel at section B B. Okay. So, let us now write for steady state steady flow process between sections A and B B. What we can write? We can write H A plus C A square by 2 equal to H B plus C B square by 2. So, this is enthalpy of at section B B, enthalpy of the flowing air stream. See, we have written this because there is no heat and work interaction. So, that is we have written, that is in absence of any heat and work interactions. Okay. So, that is can write. Now, that is enthalpy of air stream at section A, this is the velocity of air stream at section A, that is obviously higher than the velocity at section B B, because that is what we need. We need to increase the velocity of air at section B B, and that is why we have provided venturi. So, now C A is much less than C B, because cross sectional area of A is much larger than of B B. Okay. And also this section is the air at this section is in atmospheric condition, and this section A is far away from section B B. Though we could not show it properly in this schematic depiction, but section A is first away from section B B, and this is the air at that section is in the atmospheric condition. So, this is what we have written. So, basically if this is the case, the consequence of this is that we can write C A is almost equal to 0 as compared to C B. So, what we can write? We can write H A equal to H B plus C B square by 2, and from there we can calculate C B equal to 2 into H A minus H B. Okay. So, if we assume that air, though it is not purely air fuel mixture, but we can assume that the working fluid there is behaving just like an ideal gas, and if that is the case, for an ideal gas assumptions, we can write C B is equal to 2 C P T A minus T B. See, that means velocity is nothing but 2 C P into T A minus T B, but you know that T A and T B, T A is the atmospheric temperature of air, but T B we need to calculate. So, we really do not know what is the temperature of air at section B B. Okay. So, if we now we had seen that we have connected an U-tube manometer at section BB, so we can measure the pressure drop. Okay. So, if we measure the pressure drop, then perhaps we can measure the pressure at section BB. By measuring pressure at section BB, we can relate TB, or in other way, this TB, TA is known, but TB can be written in terms of the pressure at section BB. Okay. So, for this isentropic expansion, here we can write, assuming the process is isentropic, process that is between sections A and BB. So, assuming that process is isentropic between sections A and BB, we have also already assumed ideal gas assumptions, and we are also assuming that the process can be modeled by an isentropic process. Then we can write TB by TA. Okay. So, equal to PB by PA power gamma minus 1 upon gamma. Okay. That means, so this CB can be written under root 2 CPTA into 1 minus PB by PA power gamma minus 1 power half. That means, if we take TA outside and we can take under root 2 Cp TA outside, because Cp is known, TA is known, and now we can write Pb by P. Pa is the atmospheric pressure, that is pressure at section A, and Pb that is that needs to be calculated by using simple float that U-tube manometer. Okay, then what would be the mass flow rate? So, mass flow rate of air m dot A, that is equal to, because we need to calculate mass flow rate of air. So, this is air, this A stands for air, I am writing AIR, and that is at section BB. If I use suffix A, that will stand for section A, but to avoid any confusion I am writing m dot air, that is mass flow rate of air, and we are interested in calculating the mass flow rate of air at section BB. So, that is rho B into area B into velocity into Cb, rho A into velocity, rho into AB into Cb. AB that we know, because that is what we are designing the Venturi. Rho B that we also need to know, because rho B is not calculated, but we can calculate pressure by using the manometer that is connected at section BB, and already we have calculated Cb. So, if we write this expression, eventually we are getting, so this is AB into rho B into AB under root 2 Cp into Ta into 1 minus Pb by Pa power gamma minus 1 upon gamma power half. So, this is gamma minus 1. So, this is gamma minus 1 upon gamma. Okay. So, this is what we can write, very simple expression. Now, it is not complete, this expression is not complete, because we can't calculate mass flow rate provided we do not calculate rho B. So, in this expression you can understand that we know AB, that is the cross sectional area of section BB, that is obtained from the design of the Venturi. Cp is known, Ta is known, Pb and Pa, this ratio is also known, but we also need to know rho B to close this equation. So, also we can write for an isentropic process. So, for an isentropic process, because that is what we have assumed. So, we have assumed that the air fuel mixture or simple air can be, because we are interested in calculating mass flow rate of air at section BB, maybe after a few cycles of operation at that section it is not purely air, rather it is a fuel air mixture. So, we are assuming that that particular fluid that is mixture of air and fuel, maximum air, very less amount of fuel is there, can be considered to be an ideal gas, and we are assuming that the entire process can be modeled by an isentropic process. So, for an isentropic process we can write T, which is proportional to P power gamma minus 1 upon gamma, that we can write from the previous expression, because we had written Tb by T is equal to Pb by Pa. Now, what is P? That is rho RT. So, that is proportional to rho RT power gamma minus 1 upon gamma. So, our objective should be to write rho in terms of T, because if we can write in terms of Tb by Ta, then we can relate in terms of Pb by Pa. Okay. So, what we can write from this expression, because this is T power gamma minus 1 upon gamma, if we take this side, then we can write T power 1 upon gamma is proportional to rho power gamma minus 1 upon gamma. Okay. So, that means T is proportional to rho power gamma minus 1. So, this is what we can write from this. So, if we go to the we go to the next slide, we can write. So, that is T is proportional to rho power gamma minus 1, that therefore, Tb by Ta is proportional to, or I can write this Tb by Ta is rho b by rho a power gamma minus 1. So, we can write rho b is equal to rho a into Tb by Ta power 1 upon gamma minus 1, that is rho a into Pb by Pa power gamma minus 1 by gamma. So, that is 1 by gamma, gamma minus 1 by gamma into 1 upon gamma minus 1. So, if we write one step further, that is rho a into Pb by Pa power 1 upon gamma. This will get cancelled out. So, this is the expression of rho b. So, now knowing the value of rho b, we can close that equation, that is the mass flow rate of air. So, we can write here, that is mass flow rate of air m dot air equal to rho a. Now, rho b is equal to rho a. So, rho a into Pb by Pa power 1 upon gamma under root 2 Cpta into Ab under root 2 Cpta into 1 minus Pb by Pa power gamma minus 1 upon gamma power half. So, this is the expression of mass flow rate, that is what we wanted to have, right, because so for a given dimension of the venturi, that is AB, ambient condition we know, because Cp Ta and Pa is known, we can measure Pb by connecting this U tube manometer that we had seen in the schematic depiction. We can calculate what would be the density of what would be the mass flow rate of air at section Bb. We can write this expression further in a closed form. So, let me write here. So, m dot air is rho a Ab under root 2 Cpta, and that means we are trying to take this component inside this root, and we can write this is Pb by Pa is 2 by gamma, that is minus it would be P b by P a power gamma plus 1 upon gamma power half. So, this is the mass flow rate of air, right. So, now you can see in this expression we have expressed the mass flow rate of air, that is the flow rate of air at section B b in terms of all known quantities, because we know P a, the pressure at section A, that is the atmospheric pressure, atmospheric temperature T a. We also can calculate density of air at section A, C p is known. This A b is only the, this is very important, this A b is the Venturi area. So, that someone can design accordingly to obtain this much. So, what would be the amount of mass flow rate, that of course, as per the requirement of the load or demand of the engine, we can design Venturi, so that we can get the desired mass flow rate. And this mass flow rate is, again let me tell you, because we have assumed that the mixture of fuel air, which is neither purely air at section B b, to be an ideal gas, and we have assumed that the flow is an isentropic process. But you have seen, you have studied in thermodynamics that a process is isentropic, that is frictionless process, and there is no heat interaction, no heat transfer. But though there is no heat interaction between the in the process, the process is not involved with any type of heat and work interaction, but we cannot trivially ignore the frictional effect, because though the viscosity of air is very small, still it is bounded by the solid walls. So, if we go to the schematic depiction, that you know that when air is trying to flow over this, so there is a constricted passage, moreover solid surfaces are there, so boundary layer will form. So, basically we cannot trivially ignore the frictional effect. So, accounting for this particular aspect, the mass flow rate that we could write over here is not the actual mass flow rate, rather this is the ideal mass flow rate. So, this mass flow rate is the ideal mass flow rate. Why? Because accounting for the frictional loss. So, this is the ideal mass flow rate. Now, to get the actual mass flow rate, we need to multiply this quantity with one coefficient that you have studied in your fluid mechanics course, that when there is we had studied about Venturi meter, orifice meter. So, this is as good as Venturi meter, that we are providing Venturi to reduce the area, flow area, so that the velocity of the flowing fluid can be increased to reduce the pressure. So, that pressure difference is needed to have a flow of fuel from float chamber to the Venturi. So, Venturi section. So, to obtain actual mass flow rate, that is m dot air actual equal to m dot air ideal multiplied by CDA. So, this is m dot air ideal. So, you can understand that this CDA equal to m dot air actual divided by m dot air ideal. So, this is known as discharge coefficient. So, this is the discharge coefficient. So, very important that we could establish the expression of actual mass flow rate that we are going to get at section BB, and if that mass flow rate is obtained, ensuring that the flow rate of fuel should be sufficient to meet the demand of the engine. So, we are getting this much amount of mass flow rate, and to obtain this mass flow rate we had to provide Venturi that we had seen in the schematic depiction, right. So, the carburetor is provided with this Venturi, to reduce the cross sectional area at section BB, and the amount of the mass flow rate that is obtained at this section BB should be sufficient to meet the demand, as well as the mass flow rate also would be enough to ensure that the fuel that would be supplied from the float chamber to this particular section is also sufficient. So, basically we need to design the venturi in such a way that there will be flow of fuel from float chamber to this venturi. That means, mass flow rate of fuel should be adequate for the requirement, that is that will vary from that will vary with the load of the engine, and also a reduction in cross sectional area will increase the velocity, but if the area is reducing, so basically mass flow rate also will reduce, mass flow rate of air, but you also need the designer should be careful while designing the system that mass flow rate of air should not be compromised. So, this is what is important to have the optimum design of the venturi. So, to summarize today's class, to summarize what we have discussed in today's class, we have discussed about the operation of a simple float type carburetor, then we have analyzed the flow of air as well as fuel from float chamber into the venturi, and finally, we could establish the expression of the mass flow rate of air. And with this I stop here today, and in the next class we shall discuss about the mass flow rate of fuel, which is also important to know pertaining to this